Alright, so this video is going to be covering Chapter 11, Section 4, which deals with diffusion and effusion. Now, the first thing we have to know is we have to recap the definition of temperature, which is essentially a measure of the kinetic energy, or the energy due to movement of molecules. Remember, molecules don't just sit there, they're sort of vibrating up, down, left, right, in, out, etc. The whole time. And kinetic energy, even at a molecular level, is given by the formula mv squared over 2, where m is the mass of the object, in this case a molecule, and v is the velocity of that object, once again a molecule. Now what you hopefully can see is that at the same temperature, two different molecules, let's say a big one with a large mass m, and a small one with a small mass m, will have two very different velocities despite having the same temperature. This one will move a lot slower than the smaller one, because the smaller one has to make up for its lack of mass with an increase in velocity to achieve the same temperature, according to this formula. Now we can express both their kinetic energies and therefore their temperatures, which will be equal, using this formula we've written down earlier. So this will be mass 1, velocity 1 over 2 equals little mass, velocity 2 squared, once again over 2. And these two are equal because they are again at the same temperature. Now before we go any further, we have to talk about effusion. And effusion is essentially a measure of how quickly a gas leaks out of a tiny hole. So let's say you have a bunch of molecules. If these molecules are going fast, they're going to leak out quickly because they're going to have more collisions per second with the side. However, if they're more massive, they're beefier molecules, then they're going to have the same kinetic energy, however they're going to be moving slower and therefore have less collisions with the side and leak out at a slower rate. So you can say that the rate of effusion is somewhat proportional to the velocity of a molecule. Now because we know that rate of effusion is proportional to its velocity, we can do some canceling. First of all, get rid of these 2's, and in these above equations we can essentially replace them with the rate of effusion instead of the velocity. So you get big mass 1 times its rate of effusion squared equals little mass times its rate of effusion also squared. Now once you do some rearranging, you can see that mass 1 over mass 2 will both equal the rate of effusion of 2 squared over the rate of effusion of 1, also squared. Alright, so having cleared that up, we'll get on to our final step, which is that the rate of effusion of, say, gas 2 over the rate of effusion of gas 1 is equal to the square root of mass 1 over the square root of mass 2. And this is something that is known as Graham's law of effusion. And as you can see, if you know the two rates of effusion of the two gases, which you can determine from experiment, and you know one of the masses of the gases, you can then use those three variables to determine the mass, that is the molar mass, of an unknown substance. Alright, so just do one quick sample problem with Graham's law of effusion. We'll compare the rates of effusion of hydrogen gas to those of oxygen gas. So I have Graham's law written right here, and all we have to do now is plug in the values. So for example, we'll say effusion 1 will be the effusion of hydrogen, and rate of effusion 2 will be the effusion of oxygen gas. Now you have to plug in the corresponding masses to make sure you get the correct answer. So the molar mass of O2 is about 32 grams, and the molar mass of H2 is about 2.02 grams. Now, using these two values, we can plug them in under the radicals, and once you do the math, you'll see that the units cancel, both grams, and you end up with this constant. Now, what does this mean? It means that the rate of effusion of hydrogen is 3.98 times faster than the rate of effusion of oxygen. If you look over here, you can see you get this ratio, and this means that hydrogen effuses 3.98 times faster than the oxygen does on the bottom.